Welcome to the Deep Dive. Today we're going to be taking a look at quantum computing,
Okay. Sounds good.
a field that's generating a lot of buzz these days,
Yeah,
but also a fair share of skepticism.
definitely.
We've got a whole stack of research articles here,
Yeah.
and we're going to try to sift through the hype
Right.
and really figure out where this technology stands.
Yeah,
Right.
that's a really complex landscape for
Yeah,
sure,
yeah.
with rapid advancements happening alongside
Right.
some pretty fundamental challenges.
Right. So for our listener out there
Yeah.
who might be hearing about quantum computing in the news, but isn't quite sure what to make of it all,
Yeah.
let's start with the basics.
Okay.
What are quantum computers?
Sure.
And how are they different
Yeah.
from the computers we use every day?
So,
Yeah.
well, at the heart of it
Yeah.
is the qubit
Okay.
instead of bits,
Right.
which can be either a 0 or a 1.
Right. A 0 or a 1.
Quantum computers use these things called qubits,
Okay.
which can exist in a superposition,
Superposition.
a state where they're both 0 and 1 at the same time.
Wow. Okay, so they're both at the same time.
Yeah, it's kind of a
So it's not even like
mind-bending concept.
it's not even like a coin flip where it's 50-50.
Right.
It's literally both.
It's both at the same
They're
time.
at the same time.
And that's what allows them to perform calculations in ways that are just impossible for classical computers.
Okay, so that's where the
Yeah.
potential power comes from.
Right.
Okay. But I keep hearing this term quantum supremacy
Yeah.
thrown around.
Mm-hmm.
What does that actually mean?
Yeah.
And has it been achieved?
Quantum supremacy refers to the point
Oh.
where a quantum computer can solve a problem
Mm-hmm.
that's practically impossible
Okay.
for a classical computer to solve
Yeah.
in any reasonable time frame.
Okay.
Google claimed to have achieved this back in 2019.
They did.
But there's been debate about whether their experiment truly met the criteria.
Interesting.
And even if it did,
Yeah.
the goalposts keep moving as classical algorithms improve.
So it's a
Like-
bit of a moving target.
Yeah,
We can't just say,
exactly.
okay, quantum computers are now better than classical computers.
You can't just make a blanket statement because it really depends on
Yeah.
the specific problem you're trying to solve.
It depends on the problem.
Yeah.
Okay.
And it's important to remember that
Yeah.
even as quantum computers are advancing,
Right.
classical computers aren't standing still.
Of course not there.
Researchers are constantly developing faster, more efficient algorithms.
Yeah.
So the gap between the two is always evolving.
Right. So it's a constant race,
It is.
which brings us to the challenges, right? Because even if we can build quantum computers
Yeah.
that outperform classical computers
Yeah.
for certain tasks, there are some pretty significant hurdles to overcome.
Absolutely. One of the biggest is scalability.
Okay.
Building quantum computers
Yeah.
with a large number of qubits is incredibly difficult.
Okay.
Each qubit is extremely sensitive to its environment,
Okay.
and maintaining their stability as you add more and more qubits
Right.
becomes exponentially harder.
Wow. So like
It's
I've heard it compared to trying to build a house of cards in a hurricane.
That's a good analogy.
Yeah.
The qubits are incredibly fragile,
Yeah.
and any interaction with their surroundings can cause them to lose
Oh, wow.
their quantum properties,
Okay.
a process known as decoherence.
Decoherence. Okay.
Yeah.
So it's not just about
Yeah.
building bigger machines. It's about building them in a way that shields these qubits from any kind of disturbance.
Right. Researchers are using techniques like
Right.
extreme cooling and magnetic shielding
Okay.
to isolate the qubits from their environment. But it's a constant battle against decoherence.
It's a constant battle.
Wow.
And on top of that, you've got the issue of error correction.
Error correction. Right.
Because these qubits are so sensitive,
Yeah.
they're prone to errors,
Yeah.
which can completely mess up a calculation.
Wow.
So to make quantum computers reliable, we need robust error correction techniques.
Right.
But these techniques themselves require additional qubits,
Oh, wow.
which brings us back to the scalability problem.
Right back to the beginning.
Yeah, it's a bit of a catch-22.
So we've got scalability, we've got decoherence,
Yeah.
we've got error correction,
Hmm.
all these interrelated challenges
Right.
that researchers are grappling with. It's
Yeah.
no wonder there's skepticism.
Yeah, there are some prominent voices in the field
Yeah.
who have expressed doubts,
Interesting.
pointing to the fundamental limits of physics
Yeah.
and the sheer complexity of engineering such systems.
Right.
But there's also a lot of optimism
Okay.
and a tremendous amount of research and development happening
Right.
to overcome these challenges, to try to figure it out.
Yeah.
Yeah, I'm curious to hear more about the arguments
Yeah.
from both sides.
Sure.
Who are some of the key figures in this debate?
Okay.
And what are their main points?
We can dive into that.
So we've got these significant hurdles in building the machines themselves.
Right.
But let's shift gears a bit.
Yeah. Okay.
And talk about the potential,
Sure.
the why behind all this effort.
The why.
What are some of the areas where quantum computers could really revolutionize things?
Well, one area that holds immense promise is drug discovery.
Okay.
Imagine being able to design personalized medicine
Wow.
tailored to an individual's genetic makeup.
Okay.
Quantum computers could simulate the interactions between molecules with incredible precision,
Oh, wow.
allowing us to see how a potential drug would actually interact with the body
Really?
before even synthesizing it in a lab.
So instead of that long and expensive process of trial and error
Exactly.
that we have now, we could develop highly targeted therapies
Yeah.
with fewer side effects.
Severe side effects.
Maybe even cures for diseases that are currently considered incurable.
That's the hope.
Wow.
It really could transform medicine as we know it.
Yeah, that's incredible.
And another area where quantum computers could have a profound impact is material science.
Material science. Okay.
Imagine being able to design new materials,
Okay.
atom by atom,
Wow.
with specific properties.
So we're talking about more than just stronger plastics or lighter metals here, right?
Right, we're talking about materials with completely new properties that we can't even conceive of right now.
Like what?
Superconductors that work at room temperature,
Okay.
leading to lossless energy transmission,
Wow.
or ultra-efficient solar panels that capture almost all of the sun's energy.
That would be incredible.
The possibilities are mind-boggling.
It sounds like we're talking about a future
Yeah.
where we're not just discovering new materials.
Right.
We're actually creating them.
Yeah.
Almost like playing with molecular Legos.
That's a great way to put it.
Wow.
And then there's cryptography,
Cryptography.
a field that could be completely upended by quantum computing.
How so?
The encryption methods we rely on today could be cracked
Oh, wow.
by a sufficiently powerful quantum computer,
Okay.
which is a bit unnerving.
Yeah, I've heard about that.
Yeah.
So it's a potential threat to cybersecurity,
Right.
but also an opportunity to develop new,
Exactly.
more secure encryption methods.
It's a bit of an arms race,
Right.
with researchers working hard to develop quantum-resistant cryptography.
Oh, wow.
It's crucial that we stay ahead of the curve to ensure the security of our digital world in the quantum age.
Right. So drug discovery materials, science, cryptography.
Yeah,
Those are some pretty big areas
huge areas.
with potentially world-changing implications.
Absolutely.
But I'm guessing there are still challenges
Oh, absolutely.
in actually applying quantum computing to these real-world problems.
It's not just about building the machines.
Right.
It's about developing the software and algorithms
Okay.
that can harness their power.
Yeah.
And one of the biggest challenges is that we need new algorithms,
Okay.
specifically designed for quantum computers. They
Yeah.
work in a fundamentally different way than classical computers.
Right.
So we can't just take existing algorithms
Right.
and run them on a quantum machine.
It's like having this incredible new tool,
Yeah,
but we're still figuring out how to use it effectively.
exactly. And then there's the issue of data processing.
Okay, data processing.
Quantum computers are great at certain types of calculations,
Yeah.
but loading and manipulating large data sets
Right.
on a quantum computer is a complex and time-consuming process.
So it's not just about the raw processing power.
Right.
It's about the whole ecosystem
Exactly.
of data management
Yeah.
and input-output operations.
Right. And this is where the interplay between classical and quantum computing becomes really interesting.
Okay, interesting. How so?
It's unlikely that quantum computers will completely replace classical computers.
Okay.
Instead, we're likely to see a future
Mm-hmm.
where they work together,
Okay.
each playing to their strengths.
A kind of hybrid approach.
Yeah.
Where classical computers handle the heavy lifting of data processing
Right.
and quantum computers are called in
Yeah,
for the specialized tasks they excel at.
precisely. And that brings us to
Okay.
a really fascinating concept called dequantization.
Dequantization. Okay, I have to admit.
Yeah.
I'm not familiar with that one.
It's a bit of a mind bender,
Okay.
but essentially it refers to the process of developing classical algorithms
Okay.
that can achieve the same results
Wow.
as quantum algorithms, or
Yeah.
at least come very close.
So even as we're striving to build these incredibly complex quantum computers,
Yeah.
some folks are finding ways to solve the same problems on our good old-fashioned classical machines.
Exactly. It turns out that some problems
Yeah.
that were initially thought to be uniquely suited for quantum computers
Right.
can actually be tackled quite efficiently
Wow.
by clever classical algorithms.
So it's like this
Yeah.
constant game of leapfrog
It is.
with quantum and classical computing pushing each other forward.
Yes, and it's a testament to the ingenuity of computer scientists.
Right.
And the fact that our understanding of both quantum and classical computation is always evolving.
It's always changing.
Always evolving.
Wow. So dequantization's like a reminder that this field's always evolving.
Yeah.
And the lines between what's uniquely quantum
Right.
and what's achievable classically
Right.
are always shifting.
Exactly. And it highlights the importance of
Yeah.
not getting too caught up in the hype.
Right.
Quantum computing has enormous potential,
Yeah.
but it's not a magic bullet.
Right. We've talked about the challenges
Yeah.
of building the machines themselves, the need for new algorithms and data processing techniques. It seems like there's still a long way to go
Yeah.
before we see widespread practical application.
Yes. But the progress being made is remarkable.
Yeah.
It wasn't that long ago
Yeah.
that quantum computers were purely theoretical.
Right.
Now we have working prototypes,
Wow.
and researchers are making significant strides every year.
So even if practical quantum computing is still some years off,
Yeah.
the research being done today is already leading to advancements in other areas, right?
Absolutely. The quest to build quantum computers is pushing the boundaries of physics,
Right.
materials, science, computer science,
Yeah.
and this spills over into other fields,
Okay.
leading to new discoveries and innovations that
Yeah.
we might not have seen otherwise.
That's a great point. It's like this rising tide
It's-
that lifts all boats.
Precisely. And as we wrap up
Yeah.
this deep dive into quantum computing,
Mm-hmm.
I think it's important to step back and just appreciate the sheer wonder of it all.
You're right. Here we are trying to harness the
Yeah.
strangeness of quantum mechanics
I know.
to build machines
It's crazy.
that can solve problems
Yeah.
that would take classical computers billions of years.
It's mind-boggling.
It really is. And who knows what the future holds?
I know. It's so exciting.
Maybe one day we'll look back at our current understanding of quantum computing
Yeah.
and laugh at how primitive it was.
Totally like someone in the 1950s trying to imagine the internet.
Exactly. We're just scratching the surface here
Yeah,
of what's possible.
for sure.
And that's what makes this field so exciting.
It is. It's such a fascinating field.
So for our listener out there
Yeah,
who may be feeling a bit overwhelmed by all this information,
right.
what would you say is the key takeaway?
I think the key takeaway is this.
Okay.
Quantum computing is a journey, not a destination.
Okay.
We're still in those early stages,
Yeah.
but the potential is truly transformative.
It's a field that demands patience, curiosity,
Absolutely.
and a willingness to embrace complexity,
Yeah,
but the rewards could be immense.
they could be incredible.
Well said. And on that note, I think we've reached the end
Yeah,
of our deep dive
it's been fun.
into this fascinating world of quantum computing.
For sure.
Thanks for joining us.
It's been a pleasure.
And remember,
Until next time,
stay curious out there.
keep exploring and never stop asking questions.